Hello, and welcome to Let's Talk Clean Air, where we find out more about how clean air can affect the quality process for you and the workplace. I'm your host, Jacob Stewart, and in this episode, we're going to learn more about the ASHRAE Standard 199 and how it relates to the efficiency of your dust collector. With me today is Camfil APC's Daniel Vanguilder. How are you doing today, Daniel?
I'm doing great. How about yourself?
Doing pretty good. To start things off, can you tell me more about your position and what you do here at Camfil?
Yeah, sure. I started off at Camfil working as a lab tech in the dust sample lab. So I was analyzing customers' dusts. They're sending in and recommending proper air to cloth and filter recommendations. Since then, I transitioned more into a filter design engineer role, and I've been doing that ever since. So I've been here roughly 11 years.
Okay, nice. So we'll go ahead and get into the questions about the ASHRAE Standard 199. First off, could you just tell us a little bit about it, just kind of like what it is and its background, just kind of in general?
So the ASHRAE 199 was needed because the only test performed on air filtration for the dust collection side, the only test performed was the ASHRAE 52.2 test. So we've been running ASHRAE 52.2 tests in-house on all of our filters for many years, mainly for R&D purposes and for quality checks. And the ASHRAE 52.2 filter test will give you good information about the efficiency of a filter and the pressure drop. That's good information. However, it doesn't take into account a dust collector filter's life with regards to the main difference being that the ASHRAE 52.2 test was designed for a static loaded filter, essentially a filter that you would load with dust and then throw away. So think of like your furnace filter at home. So this is not how dust collectors operate. Dust collectors load the filter up with dust and then clean it off and rinse and repeat. So the issue is there are filters that perform well in the ASHRAE 52.2 test, has good efficiency, low pressure drop, but it doesn't clean well. It doesn't release the dust. So that's really what brought forth the need for the ASHRAE 199 test. It takes into account the not only the unit and the filters, but how well that filter cleans. When we call it like that cleaning, so more like a static loaded test is the ASHRAE 52.2, and a dynamic loading test is the ASHRAE 199.
Okay, so the 199 basically covers more of your bases and gets more in depth than the other one would, I guess you'd say.
Correct. The 52.2 tells you, okay, we have a really good filter here. It's good filter media. It may perform poorly in a dust collector. Whereas the 199, you know that it's done well in dust collector, it's been tested. It does release dust properly. It does give you a long filter life.
So this, correct me if I'm wrong here, this is how you basically know whether a dust collector is ready for the market, essentially.
So we do it. We use our own test rig here for our own internal R&D, and yeah, so that is how we. That's like the metric. And there's many different parameters that we look at, but that is how we do our internal research to know how to optimize like the pulse cleaning system, how to optimize the filter design, how to optimize which vendor's hardware performs the best. So we try to take all that into account and utilize that in conjunction with our filter design to get the best performance we can.
Okay. So you kind of answered this a little bit already, but what types of dust collectors are typically covered under the standard 199?
It's essentially anything that is reverse pulse cleaned or like a pulse jet. So that is bag filters, cartridge filters, and envelope filters.
Okay. So how is this test performed?
Okay, so this test has many different stages, and the different stages are to simulate the different real life ways that a dust collector can operate. So if you were to go and install a new dust collector in the field, the first thing you would do would be load it up with dust. So the first stage of the test is just dust loading. So essentially, you have your brand new cartridges installed, and you're going to feed dust up to a specified high DP set point. And the DP set points are actually specified by the testing body, or not the testing body, but the testee, I guess. Like Camfil would set up, we would set up our own. Hey, we want to operate this at 2 inches and 1 inch, typical. But other people may want to operate at 4 inches and 2 inches, or just whatever you want to do. Once you have that parameter set, then you will load dust up to that set point, and that's the first stage. Once you load up and you get your curve that goes up and you hit the parameter that you set, like for us would be 2 inches in most cases, that ends the first stage of the test, which is the dust loading or initial dust loading. And so that part of the test actually tells you a little bit already about the performance of the filters, because some of them will take a longer time just about filter design or about other things that you've changed in the test. But yeah, that covers pretty much the first part.
Okay. And before you go any further in it, just a question about the initial dust loading. Does it matter? Like, do you ever test it with different types of dust?
No, and I should have mentioned this earlier. So the test has many constants that have to be held from test lab to test lab, have to be held constant. So that is the test dust is calcium carbonate. That was chosen because it's a manufactured dust. So it is, and it's readily available, and the particle size is known, and it doesn't, since it's manufactured, it doesn't deviate very much from those particle size. So it's a readily available known particle size. So that's the test dust that everyone has to use. And then the other constants are you have to feed that test dust at 1 grain per cubic foot. So whatever CFM you test at, whatever airflow you're at, you have to do the calculation so there's 1 grain per cubic foot. So and that's basically your inlet loading concentration. That has to be held constant because you could get around and make things look better if you fed it a lot less dust loading, then you'd have better filter performance, so on. So we're holding the dust type, the dust feed, and then there's also parameters for your temperature and humidity. The temperature it just has to be within a certain range. It's not as important, but as the temperatures change, you will have to. It affects how your dust reacts. The humidity is actually pretty important because if the humidity gets too low, the dust can become more electrostatically charged. If it gets too high, then at that point it wants to agglomerate and clump up a little bit. So it changes the physical properties of the dust. So that's also a parameter you have to have as far as a lab condition to run the test. You can only pulse 25% of your media at once, which usually means you have to use 4 cartridges for this test. So pulsing one at a time to allow the other 3 filters to let the airflow go through. The rest of the test, the unit and the hardware are considered in this test a black box. So say we design a new unit, then we would go in there and we would hook it up to the ducting and the fan and whatever filter cartridge we use. We might use those same cartridges in that filter, but we might want to swap out the hardware or the black box and use something else. And then it would test. At that point, you'd be holding the filters constant and testing more of the hardware side. So it's not only testing the filters, but also the hardware. The second stage is once it's achieved that high DP set point, then you'll pulse on demand for a time. I want to say it's 4 hours. After pulsing for those 4 hours, then it will go from on-demand pulsing to a set of 24 hours of continuous pulsing. What we're trying to achieve by going through these different pulsing stages is, manufacturer A and manufacturer B operate completely differently. Manufacturer A only does on-demand pulsing at the high and low set points. Once it gets up to 2 inches, it pulses down to 1 inch and just rinse, repeat. Manufacturer B only does continuous cleaning. So they put the system in there and it just pulses continuously over and over, which drops the pressure drop. There are certain times where manufacturer, actually either one of those manufacturers use different types based on the application. Certain applications that can handle it, you will pulse on demand to save on compressed air. Some applications are so difficult that you actually have to pulse continuously just to achieve any decent filter life. So back on the stages, again, you have initial dust load, you have an on-demand stage for 4 hours, you have a 24-hour continuous pulsing section, and then you have the remaining, I believe, 20 hours of on-demand pulsing. And those are all like the dust feeding stages and the different operating parameters. By looking at these different stages, what we're really looking for, stage 3 and 4 are pretty important. I think 4 is probably the most important for us. Stage 3 can give you some interesting information too, because as you're looking at a 24-hour period of continuous pulsing, what you're really concerned is that slope. Is there a slope? We've seen some that pulse 24 hours at that dust loading and airflow, and it's a flat line. It never really increases or degrades the DP. If there is a slope, then that means that eventually the filter is going to, it'll keep operating until that keeps climbing higher and higher, and then it just means it can't maintain that pressure or that dust load and that pressure.
So how long would you say this entire process takes as a whole, typically?
Most of the full tests that we do, that we performed, are roughly 40 to 50 hours. That is highly dependent on how the filters perform. In those initial stages, like stage 2, stage 3, where you're feeding dust, if you see the DP start trending upward, it will then actually, it can fail to, I won't say fail, it stops the test at that point. It's a marker or an indicator that, hey, this filter is not going to make it the rest of the test. So some of them have stopped short, but most of the case, everything that we've done has lasted 40 plus hours.
We've gone over 4 stages for the test so far, and I believe there are 6 in total. Is that right?
Correct. So after you do all of the testing for the dust loading, then another thing that happens in the real world is you have maintenance or an energy or a power issue, and you lose your compressor or compressed air. So you're still running, feeding dust, but you're not pulsing off your filters for like a day or two. Then what happens? Well, your pressure spikes. So stage 5 of the test is called the upset condition, where we feed dust to the filter and load it up to typically 10 inches. And this is also a test on the cartridge filters too, to make sure that they can handle that type of negative pressure, which isn't much on the cartridge filter, but it's still a good test to make sure that the media and everything can handle 10 inches of water gauge. So once we do that, that completes stage 5, and then you'll go to stage 6, which is the recovery stage. So what we want to test then is, okay, our filters are loaded up to 10 inches. Let's try to clean them down. And this is similar to an offline pulsing stage. And what we're trying to learn is if the filters are going to release that dust after loading up with 10 inches of water gauge. So you'll pulse 10 cycles at 25% airflow. And then at the end of that, you will start feeding dust again and get like a final pressure after everything is done. So a summary of the test is more like a filter life performance test. It's a performance based. So you're gonna load your filter up to 2 inches. I keep saying 2 inches because that's what we're usually do in the lab.
Right.
It could be 4. It could be whatever you want. So you're gonna load it up to your specified DP. You're gonna pulse it on demand for a short period. Then you're gonna pulse it continuously for 24 hours, and then back to another period of on-demand pulsing. And the reason for that being split is we just want 24 hours of on-demand and 24 hours of continuous pulsing, so that you have a good conditioned seasoned filter. And then after that is whenever you do the upset condition up to 10 inches, and then the recovery stage, and then like your final DP after all that's said and done. Because sometimes filters won't want to recover all the way. So whenever you go back and start feeding dust, the DP at the end of the test just starts climbing right back up again to where it was. That would be an indicator that this filter isn't going to perform well. So that's the summary of the stages, and that covers, like I said, pretty well every real life operating condition that we can see. It within like a lab condition, not any crazy upset conditions where like
Right.
Moisture or anything gets in and turns a filter to mud. We haven't done
Right, but it prepares it as much as it needs to be in order to go out into the market, basically.
Yeah, we try not to overlook any aspect of how a dust collector could be operated.
Mm-hmm. Okay. So, what performance parameters are typically measured under Standard 199?
So, the filter DP is a big one. Aside from that, then we're also looking at the downstream emissions using a spectrometer. So, the mass emissions that have gone through the filter media and made it past the filters, which would be emitted to the atmosphere if it was outside and no after filters. We're measuring that to determine the different PM counts, so PM1, 2.5, and 10. Aside from the DP and the emissions, we're also looking at the compressed air consumption. Compressors are pretty inefficient pieces of hardware, and they use a lot of energy to generate compressed air. So depending on what the cost is of your energy, the compressed air consumption can be a pretty big deal. So we want to clean the filters the best we can by using a minimal amount of compressed air to get the savings. So that's another parameter, is the compressed air consumption. Those are the three big ones that we look at. There are other smaller parameters, but those are the big three that we're concerned with.
So is the Standard 199, is that a test that customers ever approach you about, or is that something that's done more internally?
To my knowledge, we haven't been approached from a customer with this. What we use it mainly for is our own internal R&D to develop a better product. Mm-hmm. So it gives us a good baseline of how to test. It's essentially a test method to get performance metrics for our hardware and our filters.
So do you all ever use Standard 199 in conjunction with other forms of testing?
The Standard 199 gives us good data on the downstream emissions. So for different regulatory bodies, EPA, different state bodies that are looking at their emissions, we have used that PM data to get an idea of what to expect. Now, we have to take into consideration that we're using calcium carbonate to get that data. So it's not 100% accurate for that customer, but it's better than nothing. Like, it gives us an idea. Hey, are we going to be in this range? We think we are based on this data here. And here's our proof that we should be able to hit that. Typically, whenever we're doing R&D on a filter, we do like the 199 test. I'm sorry, the pre-test is like the 52.2 to make sure you have good efficiency and pressure drop. And then after that, if it does well there, then we'll continue on and build 4 filters and do the 199 test with it to see if it cleans. So that's more how we internally use that. What we have been doing a lot recently are what we're calling modified 199 tests. Mm-hmm. And it's more of, we're skipping stage 5 and 6. And some of stage, 4, 3, and what we're doing is we're loading up to 2 inches, and then we turn it on demand pulsing and see how long it takes to transition to continuous pulse. What that's telling us is we're operating at 2 inches and 1 inch, and the frequency at which it starts pulsing, basically how effective is each pulse. And as you're loading dust, each pulse gets less and less effective. And then at a certain point, you're going to transition to that continuous pulse. And then that gives us a really good metric from filter to filter to know how they're performing. Basically, this one it took it 2 hours to transition to continuous pulse, whereas this one took 6. So we use it like that a lot as well. The 199, whenever it was designed, we specifically tried not to assign a rating system or like a pass-fail. It's more along the lines of a way to compare the performance
Okay.
There's a bunch of different metrics on there from your DP to the emissions to the pulsing frequency, the compressed air usage, the initial collector pressure through it. There's so many different parameters there that you can compare that it gives a lot of good, useful information, but it's almost so much that if you're good to a consumer, they're just going to be confused.
Mm-hmm.
Whereas the 52.2, just here, you're MERV 15. And they're like, okay, that's exactly what I needed. There's no rating or anything on this. You're just looking at, I guess you would have to really be very knowledgeable of dust collection to be able to go in and interpret the report and then being able to apply that to what your application is.
You personally, do you feel that this testing process has made things easier compared to when you just had like the 52.2?
It does give good information, and there's a huge learning curve. Like, there's a lot to learn from this, especially like I said with the dynamic versus the static. You get an idea of after you run so many tests, you get an idea of what is and isn't going to work pretty early on. There's pretty early indicators of this filter's going to fail pretty soon. And if you've done so many tests, you're like, okay, it failed. I keep saying fail. I shouldn't say fail. Its pressure rose too high and got outside the bounds of the test. But at that point, you basically know that, hey, that filter, I guess if you're testing either that filter design or that cleaning system, something was not working properly. Too high, you may have had too high of an airflow, and which caused a high inlet load. There's different things to look at. But at that point, you know that you did something wrong, and then you go and change it and then try to make, a better product that will last longer. Right. That's the way that we are looking at that we use it in our lab.
All right, well, thank you, Daniel. If you'd like to find out more about this topic, simply follow the links in the show notes, which you'll find in the description of this podcast. They include links, contact details, and anything else you might need to get more information. This podcast was produced by Camfil, the world leader in the production and development of air filters and clean air solutions. You can find out more at camfil.com. Be sure to join us for our next episode, and be sure to subscribe to get notifications for future episodes. Until then, I'm your host, Jacob Stewart, and this has been Let's Talk Clean Air. Thank you for listening.